Good evening, guys. Are you able to hear me?
Yes, sir.
Okay. So, what was the last topic we were discussing?
We are doing Bohr's postulates, sir.
Bohr's postulates, right? Then we were supposed to see the expression for radius of the circular orbit. Then
So we completed till the frequency condition.
that is yes. So there are two conditions which I told you which exist, right? What are the two conditions? One is called as Bohr's quantization condition, which is MVR is equal to NH by 2 pi, and there is something called as Bohr's frequency condition where it is E2 minus E1 is equal to H into mu. Okay. Now listen. So we will see an expression for the radius of the nth orbit. Okay. So if an electron is revolving in a circular orbit, then we know that electrons, according to Bohr, will revolve only in those orbits in which the angular momentum is said to be quantized. So if I take something like this, then I know the fact that it is going to revolve in this kind of an orbit, right? Let me say this is the nth orbit in which it is revolving. Then who is providing the necessary centripetal force for this particle to revolve? That is mv square divided by Rn is equal to k into ze square divided by Rn square. Okay, mv square divided by Rn is equal to k into ze square divided by Rn square, which implies Rn is equal to kze square divided by mv square. Let me take this as equation number 1. So what did I actually apply? This is the centripetal force, and this is the Coulomb's force. Right. So Rn will be equal to kze square divided by m into v square. Similarly, we know that mvr is equal to nh divided by 2 pi, which implies v is equal to nh divided by 2 pi into m into r. Let me take this as equation number 2. Now I will take this and substitute it here. Then I'll get Rn is equal to kze square divided by mv square into, kze square divided by m into n square h square divided by 4 pi square m square into r square. This r and rn are the same. So m and m will get cancelled, which implies Rn is equal to kz square into Rn square divided by n square h square into 4 pi square. So Rn and Rn will get cancelled, which implies Rn will be equal to n square h square into 4 pi square divided by k is 1 divided by 4 pi epsilon naught, and you already have ze square. Okay. Just a minute. Oh, sorry, I made a mistake. So n square h square into 1 divided by 4 pi square is going to be like this only. Okay. Now this k, I can write it as 1 by 4 pi epsilon naught into ze square divided by n square h square divided by 4 pi square. So 1 pi will get cancelled, 4 and 4 will get cancelled, and you have an Rn here already. So this pi will go to the numerator. Rn square. This Rn and Rn will get cancelled. Yes. So 1 is equal to, you have pi z e square divided by n square h square epsilon naught is Rn, which implies Rn is equal to n square h square epsilon naught divided by pi z e square. So this is going to be the radius of the nth orbit in which a particular electron is revolving. So I can write this Rn as h square epsilon naught divided by pi into e square into n square divided by z. Now observe guys, we know that h is equal to 6.626 into 10 power minus 34 joule per second. We know that epsilon naught is 8.85 into 10 power minus 12 coulomb per meter square, coulomb per, how much is it? Epsilon 1 by 4 by epsilon naught. So you will have Newton is equal to coulomb square divided by meter square. So Newton meter square per coulomb square you will have. Similarly, you have E as 1.602 into 10 power minus 19 coulomb, right? If you take all these values and substitute it here, then you'll get the value of Rn. So pi is also there, pi is 3.14. If you substitute all these values here, then the value of Rn will come out as 0.53 times n square divided by z times angstrom. So 0.53 into n square divided by z angstrom is what is going to be the value of Rn. That is the radius of the nth orbit. Generally, if you take hydrogen, z will be equal to 1 and all other parameters are taken into consideration. Are you able to understand what I'm trying to say?
So is 0.53 denoted by something, sir? Or is it just a value?
Which one? 0.53 is a value. If you substitute all these values in this expression, right, you will get this whole thing as a constant, which is 0.53. 0.53 into n square divided by z angstrom is going to be the radius of the nth orbit. 0.53 is a fixed number. Now listen to this. If n is equal to 1, z is equal to 1. What atom is that?
Hydrogen, sir.
Hydrogen. So when I put R1 here, I get 0.53 angstrom, correct?
Yes.
Right. So this is the radius of the first orbit of a stable hydrogen atom. And the 0.53 has a name called as Bohr's radius and is represented by the symbol R0. Are you able to understand?
Yes, I understand.
So this is what happens. Okay, shall I proceed? If you guys are copying, please copy it, or else I'll proceed. Shall I proceed? Please say an yes or no.
Yes, sir.
Yes, sir.
So next one is an expression for the energy of an electron in the nth orbit. So there is an electron in the nth orbit, and our job is to find the expression for energy of that electron in that nth orbit. So generally, if you take the total energy of an electron has two properties associated with it. It has two energies. One is it has kinetic energy. The second is it has potential energy. So what is going to be the potential energy of the electron? So potential energy is going to be minus kz e square divided by Rn. Correct? How did I write kz e square divided by Rn with a minus sign? Because we know that potential energy is equal to k into q1 into q2 divided by the distance between them. So the nucleus has a charge of z into e, and the electron has a charge of e. When you multiply these two, you will get the potential energy as minus kz e square divided by Rn. So let this be equation number 1. What about the kinetic energy? Kinetic energy is half into m into Vn square, where V is the velocity of Vn is the velocity of the electron in the 10th orbit. Now see, we know this fact. mvn square divided by Rn is equal to kz e square divided by Rn square. So 1 Rn will get cancelled. Then I can write m into Vn square is equal to kz e square divided by Rn. Any doubt in this? Any doubt in this? Is it clear or not?
No doubt, sir.
So I can take this and substitute it here. Then I'll get kinetic energy is equal to kz e square divided by Rn. Now observe an important thing. Sorry, kz e square divided by 2 times Rn. But here the point that you need to observe is kz e square divided by Rn is already potential energy. So kz e square divided by 2Rn is kinetic energy. So what is the relation between kinetic energy and potential energy? Can I say kinetic energy is equal to the negative of potential energy divided by 2? Yes or no?
Yes, sir.
Right. Then what is going to be the total energy? E total will be equal to kinetic energy plus potential energy. Potential energy is U. Kinetic energy is minus U by 2. So how much will you get?
U by 2.
You will get the total energy as U by 2. But the only difference is U is how much? Minus kz e square divided by Rn, but you already have a 2. So minus of kz e square divided by 2Rn is going to be the total energy of the electron that is present in a particular orbit. Right? Now this will be equal to minus 1 divided by 8 pi epsilon naught into Rn is how much? Rn, see it from your notes and tell me. It is n square h square divided by n square h square divided by how much? N square h square epsilon naught divided by pi z m e square. Pi z e square. N square h square epsilon naught divided by pi z e square. So pi and pi will get cancelled. Epsilon naught will get cancelled. You will get minus z square danada. So this is there. No, you have z e square also in the numerator. So the z e square from the denominator will go to the numerator. You will have minus z square e power 4 minus z square e power 4 divided by 8 times n square h square epsilon naught. So this is going to be the total energy of the electron that is present with it when it is present in the nth orbit. Did I miss something? I think pi z e square m is there. M will also come. So minus z square e power 4 into m divided by 8 n square h square into epsilon naught.
Sir, could you go up, sir, before the substitution in UT? So, sir, when you're calculating the kinetic energy, we took M as 1, right, sir?
I didn't take m as 1. This value of m, there I took n as 1. I didn't take anything as 1. You're asking about m only, no?
Yes, M only I'm asking.
No, mass cannot be 1. No, mass is the mass of electron. How is the mass of electron 1 unit?
In case, sir, for kZe by 2Rn, that's kinetic energy. So M there.
That is k is 1 by 4 pi epsilon naught. Z is the atomic number of that particular atom. E is the charge of the electron, and Rn is the radius of the nth orbit. Are you able to understand?
But sir, if it's kinetic energy, it's half mv squared. So what happened to m?
That's what I wrote down. Kinetic energy is half mv square, correct? Then what is the next step I applied? Centripetal force is equal to Coulomb's force. When I apply that, I got mv
Oh,
square
okay, sir.
divided by.
Understood,
Now you
sir.
understood? Then what I did is, in the place of Rn, I substituted the actual expression for Rn. Okay.
Yes, sir. Understood.
Now you would have understood this. Now see, here again, E is 1.602 into 10 power minus 19. H is 6.62 into 10 power minus 34. Epsilon naught is 8.85 into 10 power minus 12. When I substitute all these, so mass is 9.1 into 10 power minus 31. So when I substitute all these values here, I get the total energy of the electron is equal to minus 13.6 into Z square divided by N square electron volt. Did you understand this? I'm sure you would have seen this formula in your chemistry. Minus 13.6 into N Z square divided by N square electron volt. This is there in atomic structure in your 11th standard. Okay. So this is the formula that we are going to apply to solve problems. So going forward, will you be able to answer what is the radius of the electron in the nth orbit? It is 0.53 into N square divided by Z angstrom. And what is the total energy of the electron present in the nth orbit? It is minus 13.6 into Z square divided by N square. Yeah. Guys, did you understand this?
Yeah. Yes, understood.
Okay, just give me a minute. I'll be back. Just keep copying it. So if you keep it like this, just keep verifying, okay? Right. So I think we are ready to move on to the next concept, right? So the last concept that is left out in this chapter is spectral series of hydrogen atom. So I told you in the beginning of this chapter itself that there is something called as spectral series. So what do you mean by these spectral series? It is basically spectrum. Spectrum is a word which you already know. It is light, right? So I asked you a question like this. If there is an electron in a higher orbit, and from that higher orbit, an electron is jumping to a lower orbit, then what will happen to the energy? It will get released, which is equal to h nu. What is this called as? this E2 minus E1 is equal to h nu is called something. What is it? What condition is this? This is Bohr's
Frequency
frequency.
condition.
Yes. So this is Bohr's frequency condition. Spectral series of hydrogen atoms. So when an electron a hydrogen atom jumps from higher energy level to the lower energy level, the difference in the energy of the two levels is emitted as a radiation of particular wavelength. And that is called as a spectral line. But we know the fact that the wavelength or the frequency that is associated with the spectral line, so we know that E2 minus E1 is equal to h nu. Can I write h nu as hc by lambda also? So the wavelength associated depends on between which two energy levels is the electron getting transmitted. Right? Depends upon the orbit between which the transition of electron so various spectral lines are obtained. So what will happen when the electron jumps from second to third will not release the same frequency as when an electron jumps from 2 to 1, when as the same as an electron jumps from fifth to fourth, something like this, right? So they correspond to different wavelengths depending on between which two orbits is the transition taking place. Then these different wavelengths constitute spectral series, which are the characteristics of atoms emitting them. So characteristics of atom is the property of that atom which is emitting these spectral lines. The following are the spectral lines of the hydrogen atom that we can think of. One is Lyman series, second is Balmer series, Paschen, bracket, and Fund series. So you have already heard these things. What is Lyman series? So Lyman series is something where an electron jumps from a higher orbit and ends always landing at the first orbit of that particular atom. So electron jumping from nth orbit to first orbit will give us a series called as Lyman series. Similarly, where the value of n is greater than 1. Okay. Or I can write n is greater than or equal to 2. These are the two things that are possible. Now, similarly, if an electron jumps from the nth orbit to the second orbit, then the spectral series corresponds to something called as Balmer. So in Balmer series, you have something called as H alpha, H beta, H gamma, H delta. All these lines are there. So that is only there in Balmer series. In H alpha, what will happen? Electron jumps from second to first. In H beta, sorry. I'm sorry. If an electron jumps from third to second, it corresponds to H alpha. If an electron jumps from fourth to third, it corresponds to H beta. If an electron jumps from fifth to second, it corresponds to H gamma. Okay. In this case, what will be the value? N will be greater than 3 or n will be greater than 2 or n will be greater than or equal to 3. Similarly, if an electron jumps from any orbit to the third orbit, the series that it belongs to is Paschen series. When an electron jumps from any higher orbit to the fourth orbit, we call it as bracket, and any orbit to an orbit to the fifth orbit, we call it as Fund series. Is this clear? This is already known to you guys, right? Yes or no? Are you guys there?
Yes.
Okay.
Yes, sir.
Now we are interested to find out what will be the corresponding frequency that will get emitted. Okay. So our job is to find the frequency of emitted radiation. So when I talk about the frequency, I'm going to use the formula E2 minus E1 is equal to H into nu. What is the value of E2? Minus 13.6 into Z square divided by n2 square. Correct? Minus 13.6 into z square divided by n1 square. This whole thing will be equal to h into nu. So if I take that 13.6 into z square outside, I get 1 by n1 square minus 1 by n2 square is equal to h into nu. So nu will be equal to how much, guys? Or I can write something like this. I'll write this as hc by lambda. Then what is going to be the value of lambda? Okay, listen. 1 by lambda into hc. I'll take this hc to the other side. Then 1 by lambda will be equal to 13.6 divided by h into c into z square into 1 by n1 square minus 1 by n2 square. Okay. Then this 13.6 divided by hc put together will give us a number called as r, and the z square into 1 by n1 square minus 1 by n2 square is going to be as it is. This r is what we call it as Rydberg constant, and this Rydberg constant is going to be 1.097 into 10 power 7 meter inverse. Okay. Any doubts, guys?
No doubt, sir.
Okay.
No
So,
doubt, sir.
having said that, we know that nu bar, what is nu bar, guys, by the way? What is 1 by lambda called as? Yes, you call it as wave number. So for Lyman, for a Lyman series, when electron jumps from any of the outer orbits to the first orbit, the spectral lines are emitted in a particular region which is called as the ultraviolet region of the spectrum, and they are set to form a series called as Lyman series. So generally what happens if n1 is equal to 1 and n2 will be equal to 2, 3, 4, something like that. Okay, so in the place of n1, what am I supposed to substitute? I'll put 1. Then what will happen to the wave number? It becomes r into 1 by n1, 1 by 1 square minus 1 by n2 square. So remember, they will be asked a question. Lyman series, what is the region in which the light rays are getting emitted? Similarly, when you talk about Balmer series, when you talk about an electron which jumps from the outer orbit to the second orbit, we get spectral series called as the Balmer series. Okay, and all these lines will be corresponding to a region called as the visible region. That is why we have H alpha, H beta only for Balmer series. So in this case, N1 will be 2, so N1 square will be 4, R into 1 by 4 minus 1 by N2 square. Where N2, if I put N2 is equal to 3, it will become H alpha. If N2, if I put it 4, it is called as H beta, and so on. Similarly, if I talk about Paschen series, okay, if I talk about Paschen series, then the electron jumps from a higher orbit to N2 square. Sorry, higher orbit to the third orbit. Then it becomes R into 1 by 9 minus 1 by N2 square. And in this series, it corresponds to the infrared region. Similarly, when you talk about bracket series, what will happen? N1 will be equal to 4. So if you observe in all the formula, N2 square is the same. But what is changing? N1 square. So in the case of Lyman, N1 square is 1. In the case of Balmer, it is 4. In the case of Passion, it is 9. In the case of bracket, it is 16. In the case of fund series, it is going to be 25. And this one also corresponds to infrared region. So there are three series of spectral lines which belongs to the infrared region. One is Passion, bracket, and fund series. Is that clear, guys?
Yes.
Okay. Next is, we need to understand the energy level diagram. So name suggests energy level diagram. So it is a diagram which will represent the energy of each layer or each orbit, sorry. The energy of the electron in the nth orbit of the hydrogen atom is taken as minus 13.6 into n, minus 13.6 divided by n square electron volt. Okay. Then what we can say is the energy associated with the first orbit of the hydrogen atom will be minus 13.6. How did we get it? See, since you're talking hydrogen atom, formula for energy is minus 7.6 into n square divided by z square. Sorry, z square divided by n square, electron volt. Correct? Then the value of z will be equal to 1. When I take and substitute it here, it becomes minus 13.6 divided by n square electron volt. Now, if I take the value of the first orbit, n will be equal to 1. It becomes minus 13.6 electron volt. So it is called as the ground state energy of the hydrogen atom. Similarly, if you take the energy associated with the second orbit, it becomes minus 13.6 into z square is 1 divided by n square is 4. It becomes minus 3.4 electron volt. So minus 13.6 electron volt. This will be minus 3.4 electron volt. Next is, if I take n is equal to 3, it becomes minus 1.51 electron volt. If I take n is equal to 4, it becomes minus 0.85 electron volt. And it keeps on going. When I go to n is equal to infinity, there the energy is considered to be 0. Means if the electron, that is why when the electron is pulled out of the electrostatic pull of the nucleus, then we say that the energy of that electron is 0. I mean, I'm talking about the total energy of the electron put together is 0. Okay. So it is called energy of the first excited state of the hydrogen atom, which one minus 3.4 is called as the energy of the first excited state of the hydrogen atom. So a stable hydrogen atom will have its electron at n is equal to 1. When it is excited, it goes to n is equal to 2. So the energy of the second, third, fourth excited states of the hydrogen atom will be how much? Minus 1.51 minus 0.85, and it keeps on going. And the energy of the electron in the nth orbit is going to be, sorry, infinite orbit is going to be 0. So it is seen from the above values that the energy associated with the state becomes less negative and approaches closer and closer to the maximum value 0 corresponding to n is equal to infinity. So taking the energies in a linear scale, horizontal lines are drawn which represent the energy levels of the hydrogen atom. And this diagram is what is called as the energy level diagram.
So could you go up a bit?
Sure. Want me to rotate it?
This is fine, sir.
Okay. Just go through it. You have any doubt, ask me.
Done, sir.
Done? Just give me a minute. Yeah. So after this, what we have is this thing. The last topic is de Broglie's explanation for the quantization of angular momentum, which I already explained it in the previous chapter itself. You remember, for an electron to revolve in an orbit, what should happen? So de Broglie told that particles also have wave nature associated with it. Then if you take this to be lambda, then n times lambda should be equal to 2 pi r. N into lambda according to de Broglie is h divided by mv is equal to 2 pi r. So mvr will be equal to nh divided by 2 pi. You know this? Yes or no? Last chapter we discussed our last topic of last chapter. Yes? Guys, yes or no? You remember this?
Yes, sir.
Here, wait, I'll show you for your satisfaction. The dual nature. Look, wave mechanical concept of an atom. Right, the same logic is applied here also. So there is also wave mechanical concept of an atom. Right. So with this, we are done with this chapter. So what I'll do, I'll share this notes now itself. You guys can make use of it. 1 minute. Guys, check your WhatsApp once. Did you receive it?
Sir, WhatsApp, sir.
Amman.
I didn't get
See?
it, sir.
Did you see? Check.
Now I got it.
Got it? So everybody got it, right? This is the class notes, and this itself is more than sufficient. Okay. So you guys go through these concepts.
Can you share those problems of ray optics, sir?
Problems of wave optics, huh?
Ray optics, sir.
Which problem you want?
No, sir, you had that problem sheet, no, sir.
Yeah, I
Worksheet.
solved it from the problem sheet. Yes.
Yes,
you want with solutions or without solutions?
Without solutions, sir.
You want to try it on your own. Is that right?
Yeah. Yes.
Okay, I can do it. I'll do it. Okay. So any other doubt, guys? So with this chapter is done. Okay. We have 2 more chapters. So maximum 4 more classes, and we are done with the 12th standard syllabus. After which, what I will do is I'll be discussing more number of questions. Okay. So as I told you, you be in touch with the subject and keep preparing simultaneously. Is that clear? Any other doubt from this chapter?
No doubt, sir.
No doubt. No. So tomorrow I'll start nuclei. So though we have 15 more minutes, I don't want to burden you with 2 chapters at the same time. So tomorrow I'll start nuclei. Maximum by Wednesday I'll complete it. And next Monday and Tuesday I'll complete semiconductors. With that we are done. Right. So it is now your turn to sit and practice. So that's it from my side for today. If you have any doubts, you can ask. Is that all? No doubts?
No doubt, sir.
No doubt.
Okay, then we can wind up this.
Thank you.
Thank you, sir.